This video is part of a course on food physics, of which this is the theory section. Here, this one is just the last part of a three-part series on sharp boundary approach or sharp interface approach to phase change problems like freezing, deep frying, or freeze drying. So we looked at two different approaches, the main approach and a simplified one. But the main approach itself is a simplified description of phase change problem. And in this approach, we divided the domain where phase change is taking place into two parts. One, without phase change, where phase change hasn't happened, and two, where phase change has happened. And these two domains are separated by an interface. The interface is sharp, which means it has zero thickness. That is the assumption. Now, this kind of zero thickness of an interface is true only for a pure material, like let's say water. Pure water freezing, it will have a sharp interface, but not otherwise. That's why it is an assumption. Now, this has been applied to several types of problems like freezing, where you have a frozen area, unfrozen area separated by an interface. Likewise, we have a deep frying process. This framework has been used for a deep frying process where you have a crust separated separated from a core by an interface. We also have used this, the scientific community has used this in freeze drying process, where you have a dry area and a frozen area separated by an interface. So in this framework, we have these two regions, and then how do we do this problem? In each region, we use the normal heat equation. So you use a heat equation without phase change, In both regions, we do the heat equation without phase change with its normal physics. Whatever we were using if there were no phase change, we will use that physics, and so it's just that we need to know where this interface is. Then we can use the normal heat equation in these two regions, because the phase change is happening only at the interface, not in the domains. So then again, the big problem is, how do I know this interface? That interface is found, the location of the interface is found by relating heat fluxes. So you notice heat flux from the left, this one, and to the right, normally without phase change would be the same at a location, because it's the same location. But if we have phase change, then they will not be the same, because the difference between their heat fluxes would have to do with the latent heat either given off or absorbed due to phase change. So then, by having a third equation for the interface that relates the interface velocity, how fast this freezing or freeze drying goes on, it relates that velocity to the two heat fluxes, which are known because we could use the normal heat equation with the normal physics in these two zones. So we know the temperatures in these two zones, uh, 1 and 2. So from that we can get these two fluxes and relate it to the velocity of the interface. So that's all we needed to know, is the location of the interface. And then we can do these problems. Now we can have an even simpler version. Even simpler, so that's what I mean by drastically simplified. In this one, we ignore no variation of temperature in the domain where phase change has not happened yet. So we ignore this, which means we don't even solve the equation there. So we have only one domain to solve, and of course we need to know the location of the interface. So here, the way we kind of do this, no variation in this domain, is we say from the physics that, latent heat is a lot of heat. So if all that heat has to be absorbed or removed at this interface, it takes longer than just conduction heat transfer process or the normal heat transfer process that would happen without phase change. So if this is a lot of heat that needs to be either taken out or brought back in case of thawing, then this process would be a bit slow. So we say it's slow enough that we can think of this interface at some temperature, interface temperature, where freezing or melting, let's say in case of freezing or heat transfer in freezing thawing, this stays at melting temperature, and here far away it is at the ambient temperature, and we say that this one moves so slowly that it reaches a steady state. It reaches a steady state, so we have a temperature profile that kind of looks something like that. A temperature profile that looks like that. So because of this steady state assumption, I can actually find what is the flux between these 2 points. And from those 2 fluxes, I can relate it. That gives us the rate at which heat is being transferred, and that gives us the rate at which this interface will move. So again, in this case, we can find the rate at which the interface moves. That's kind of telling us at what rate it is freezing or frying, let's say. So in both cases, this drastically simplified case or in this case, we get an equation for the interface and as a function of time, and that tells us how long is the process. The difference between them is this one is even more simplified. It makes even more assumptions than just the simplified equation of a sharp interface. We can compare the sharp boundary phase change that we just discussed with its alternative. So sharp boundary, we have this one sharp boundary where phase change happens. So its alternative is distributed phase change, where phase change can happen throughout the domain. But just because the formulation allows phase change throughout the domain, that's not what we see what we see after we solve it is phase change, instead of happening at an interface, it is happening over a region. So this is the phase change region. Okay, so that's the contrast, that it is not a sharp interface like here, but instead it's a region. So let's look at some pros and cons of it. So here then again phase change is happening at the interface, and here phase change is everywhere, but it ends up happening mostly in a narrow region. How narrow, it depends on the physics. So how do they compare? So this one is simpler. This one, meaning the sharp boundary phase change, is simpler. It can be reasonably accurate, but it is often harder to implement because of this interface tracking. So we have to track this interface, and doing that in multiple dimensions, or there can be situations for multiple interfaces, and this is quite difficult. On the other hand, for the distributed phase change, it is more realistic, and but it is more complex in terms of its formulation. And because it's complex in terms of this conceptual understanding, its implementation can also have computational challenges. So, but at the end, this will give more realistic. So this distributed phase change is discussed at length in the following modules, and again, we just said that there are pros and cons of it, but if you want to follow up with the distributed phase change, that's in the next modules under porous media. Now, relating to mechanistic formulations that are possible, mechanistic frameworks that are possible, from the very simple, like a lumped parameter, all the way to the most complex, we are here. We are talking about problems or physics situations that involve phase change. And the one that we discussed in this one is where phase change happens at a sharp interface. This has its advantages. It has it can give simpler answers, and it can give good estimates in many situations, estimates of how long does it take to freeze or how long does it take to fry. We can get it. More realistic ones have distributed phase change, but they're little more complex. Anyone interested in these distributed phase change models, they are in the follow-up videos under porous media formulations.